So the vector loop and vector loop equation, it's important to note that the nomenclature or notation that we're going to use for all of the equations derived in these next few videos and lectures have to adhere to this sort of notation. So if you look at this notation, what we have is vector 1 actually sits along this line, which you can see here. We've got vector 1, vector 2, vector 3, and vector 4. Again, important to note that vector 1, vector R1, is in line with the x-axis. Okay. So vectors have both magnitude and direction. It's not written here, but theta 1, the direction of R1 is actually 0. So we've got theta 2, theta 3, theta 4, and theta 1. All of these directions are measured from the base of the vector. Okay, so the base of the vector from a axis, horizontal, and we're moving counterclockwise, right? So base of the vector counterclockwise. This vector loop equation, remember last time in the video I said if we started here at this point and walked around in a circle along these vectors, we would add these vectors up. So the vector loop equation is going to be R2 plus R3. This is a minus R4 minus R1 equals 0. Now these are vectors. Okay? So that's the vector loop equation that we have. Real quick, when we look at vectors, we can study and use the idea of components and then angles. And the rules for drawing these vectors, vectors go from joint to joint. Okay? We start at the input link and go to the furthest point or the point of interest. This is kind of what we're looking at. You want to consider the angle of the vector with respect to something easy to establish. So the x-axis is horizontal. Okay. For each vector, we define the position of the point by the plane. The position of the vectors rx and ry. Here we go. And then angles are drawn from the tail of the vector with respect to horizontal. So angles start positive, and then angles are drawn counterclockwise. Okay. So that's some nomenclature. So let's go into the vector loop equation. So if I draw my vectors that look something like this, R1, R2, R3, R4. I've made it a little bit harder, right? Especially if I tell you that the x-axis is something like this, okay? Then theta 1 is non-zero, but we can make this a little bit easier. We can simplify this model for now and say that this is the x-axis we're looking at. The y-axis comes up at 90 degrees, and we can draw our vector loop. So what I know is it's going to be R2 plus R3 minus R4 minus R1. That's theta 2. Okay, what I'm going to have to do is draw a line here. That's horizontal. I start at this horizontal line. That's theta 3 right now. That's theta 4. Okay, so theta 1 is equal to 0, and we've got all the nomenclature down for theta 2, 3, and 4. What we can do here is now break this up into x components and y components. Okay, and we'll do that in a little bit. Another example we have here gets a little bit harder, but we've got obviously something other than a 4-bar mechanism. This is something other than a 4-bar mechanism. We can draw several vector loops. Okay, so you can have vector loops. Okay, so let's label this figure. So we label the figure. We've got link 1, link 2, link 3, link 4, link 5, link 6, and this block up here is link 7. We can label the joints A, B, C, D, E, F, G. Okay, so G being the sliding joint. And then from this, we can draw the vectors. So after drawing the vectors, we can extract out two vector loops here. We've got vector loop 1, okay, and vector loop 1 is going to be based on R2 plus R3 minus R4 minus R1 equals 0. And then vector loop 2, R2, R4 minus R3 plus R5 plus R6 minus R7 equals 0. Now, you can look at these two vector loops and understand here we've got some similar or common vectors. So when we solve for vector loop 1, which is easier because it's got 4 components in it, we can then bring this down and solve for vector loop 2. Okay. So we can go on and on and on with this system. What I would encourage you to do is compute the degrees of freedom of the system. What you'll realize is it's not a single degree of freedom system, so we might need to know more about it. Second example of vector loops is we've got this this mechanism here in the middle. We've got actually a 4-bar mechanism coupled with another 4-bar mechanism through this rigid link. So we can have multiple vector loops. We can write the first vector loop will be R2 plus R3 minus R4 minus R1 is equal 0. And the complementary vector loop will be, starting at this 04, it'll be R5 plus R6 minus R7 minus R8 is equal 0. Again, a couple notes on this. This first vector loop is easy to solve. It's easy to solve because the x-axis is in line with R1. So in this case, theta 1 is equal 0. The second vector loop is a little bit more difficult to solve because if we take the non-moving R8, okay, the non-moving R8 is not in line with the x-axis here. So what we can do is the following, and that should be lined up here with R8. We can solve for an axis kind of along this direction, okay? And then once we solve for the motion of this 4-bar mechanism, we can relate it back to the